Alright, in this video I'm going to be doing some triple integrals with spherical and cylindrical coordinates. I'm going to be working through Multivariable Calculus Homework 3.7b. And so the first one is talking about let W be the region above the plane z equals 2 and below the paraboloid. Okay, so I've got z equals 2 and z equals 6 minus x squared minus y squared. We're going to describe that region in cylindrical coordinates, and then we're going to use cylindrical coordinates to compute the volume of that region, which we're calling W. All right, so I don't really know how to draw this all that well, besides to say, all right, it's going to look like this. It's going to look like a paraboloid, but we know it's a solid. And then there's going to be z equals 2, which is going to kind of come in over here. Okay, just envision it being a flat plane, kind of like that. And this is, okay, up here, that would be z equals 6. Okay, so I'm going to say in terms of z, I'm going to start with z. Z is running from 2 up to z equals 6 minus x squared minus y squared. So I'm going to say that 2 is less than or equal to z, but z is less than or equal to 6 minus x squared minus y squared. Okay. Then, so let's think about, okay, we need r and theta, right? And so I think what I want to do is I want to look at it from above. Okay, I want to look at the situation. So in blue, I'm coming through here and just kind of coloring that. And then I'm going to give you a top view of this paraboloid plane scenario. Okay, so that's going to be my y-axis. I'm going to have to zoom out. Yeah, that's my y-axis. That's my x-axis. There's the z-axis, right? We're looking right down on top of it. Okay, and so to draw you a picture of this circle, oh, pardon me, I know it's going to be a circle, but if we wanted to figure out, y, we'd set these two equations equal to each other. 2 equals 6 minus x squared minus y squared, and we would see that that equation is true when x squared plus y squared equals 4. And we know that that represents the circle with radius 2 centered at the origin. Okay. Okay, so this is the top, this is like the view of the thing from the top. And it does, it kind of comes up to a top at z equals 6. We can't really see that, but we know what's happening. So in terms of r, in polar coordinates, r is going to run from 0 here at the origin out to 2. Okay, so I'm going to say r is between 0 and 2. And then because we're going around the whole circle, right? I'm going to say theta is between 0 and 2 pi. Okay? And so that's just us expressing W in cylindrical coordinates. All right. Okay, now I'm going to come back on these in a second. Maybe I'll say, okay. I know that I need to triple integrate dV to get volume. Okay, that's going to be equal to volume. It's just going to be an issue of writing this down. So if I've got a z depending on variables, and then r and theta, I probably need to get rid of these x's and y's. And now we know that x squared plus y squared is r squared, so this looks to me like 6 minus r squared. Right, so I'm gonna use that. So I'm gonna start the integral with dz. And I'm going to let z run from 2 up to 6 minus r squared. Okay. Then we're going to do, and then after that it doesn't really matter because it's, just constants here. So I'll do r first. R was running 0 to 2. And d theta, oh man, I almost caught myself making a bad error. Theta is going from 0 to 2 pi. Okay, and remember that dv is not just dz dr d theta. Okay, it's r dz dr d theta. Okay, just like when we were double integrating, dA was r dr d theta, dv is r dr d theta dz, or some other order of integration. Okay, so we're ready to go. So Yeah, this will be fine. I'll say that an antiderivative for r with respect to z will be rz. And I'm just going to do this here, and then I'll plug that back into the double integral. Okay, so r times z is 6r minus r to the 3. And then I'm going to be subtracting what happens when I plug in 2 for z. That would be 2r. Okay, so in total, I've got 4r minus r to the 3. Okay. And I'm integrating that from 0 to 2, 0 to 2 pi. dr d theta. Okay, yep. And now I'll be able to do this. An antiderivative for 4r with respect to r will be 2r squared. Antiderivative for negative r to the 3 with respect to r would be negative 1/4 r to the 4. Okay. R running from 0 up to 2. That's going to be when r is equal to 2. I've got 2 times 4 is 8 minus 1/4 of 16. And then when I plug in r equals 0, I'll just get 2 zeros. And so that's 4. And that's going to equal 8 pi. Okay, so that was number 1. And the volume enclosed by the paraboloids, x squared plus y squared, and 8 minus x squared minus y squared. Okay. I want to just do this with polar coordinates. Oh, I see what I'm supposed to do. Yeah, I'm supposed to do it in cylindrical. I get it. Okay. But a person could just do top minus bottom also. 8 minus x squared minus y squared minus another x squared plus y squared, integrating it over the circular region of their intersection, which I think would be the same circle that I was talking about before. Anyway, okay, so yeah, I don't know if I'm going to be able to draw you this. Okay, that's the 8 minus x squared minus y squared. And then x squared plus y squared, I think, is going to look like that. Okay, and then right, so it's going to have some sort of, this is kind of one of those like Easter egg things that you can break open and put candy inside. That's what it looks like, at least to my vision. And okay, so we are going to say, all right, this circle here that I'm going to kind of like highlight in red, break it out. I'm going to set them equal to, you could set 8 minus x squared minus y squared equals x squared plus y squared and end up with realizing that the domain we're going to be integrating over is going to be this same circle with radius 2 centered at the origin. Okay, that's the picture of that in the xy plane. Okay, now this equation is z equals x squared plus y squared, so that's going to be, in cylindrical, z equals r squared, and this will be z equals 8 minus r squared. Okay. So we know that we're going to triple integrate dv, and that dv is r dr d theta dz. Okay, but I'm going to start with z because I've got variables in there. So. Right, so dz, z is running from r squared up to 8 minus r squared. Okay. R is going from 0 out to 2. And maybe I'll just show you why that's true. I kind of said it out loud a couple of times, but I just don't want to be confused. So I'm going to say over here off to the side, 8 minus x squared minus y squared equals x squared plus y squared. That leads me to believe that 8 equals 2x squared plus 2y squared. That gives me x squared plus y squared equals 4. And I know that that's a circle with radius 2 centered at the origin. That's why I'm just letting r run from 0 to 2. Theta will go 0 to 2 pi because it's the whole circle. And, okay, antiderivative for r with respect to z will again be rz I'll let z run from r squared up to 8 minus r squared. Okay. I'll actually plug that in and say, all right, when z is 8 minus r squared, I'll have 8r minus r to the third. And then here, when z is r squared, I'll have another minus r to the third. Yeah, I don't know why I was tripping on that, but okay. Now I'm going to say that this is 0 to 2 pi, 0 to 2, 8r minus 2r to the 3 dr d theta. And 4r squared. 1/2 r to the 4th. R runs from 0 to 2. That's going to give me, when r equals 2, 4 times 4 is 16, minus half of 16. And then when r is 0, well, that'll just be a bunch of zeros. Okay, so it'll be 8. Okay, and we know how to run that integral. That's going to be 8 theta, 0 to 2 pi, 16 pi. All right, that was number 2. Number 3, convert the integral to cylindrical coordinates. Okay, yeah, we can do that. All right, 3a. -1 to 0. 0 to the square root of 1 minus x squared. And 0 to 2. Of some function dy dx. Okay. What this is saying is that z is between 0 and 2. Okay. Y is between 0 and the positive square root of 1 minus x squared. And x is between -1 and 0. And all right, so z is going to stay the same, right? Z is going to go 0 to 2 because cylindrical is polar plus z. So I don't really need to worry about the thing in red. With these, I probably need to draw an xy plane and see, like, what am I actually looking at here? Okay, the positive square root of 1 minus x squared, that's a circle with radius 1 centered at the origin, but it's only the top half because it's where y is positive. Okay. And then, what was I thinking? Oh, x runs from -1 to 0. So that means this is pretty much the region that we're talking about. So, to talk about it in terms of r and theta, r runs from 0 out to 1, because I know the radius is 1. Theta is running from pi over 2 to pi. Alright. So I might put z on the outside. R is 0 to 1. Theta is pi over 2 to pi. And f is going to stay the same. Maybe I'll say it's f of r, theta, and z. But dz, dy, dx, that's not just dr, d theta, dz. Okay, we can't just do that. We need to bring in that factor of r. So times r, this is d theta, this would be r and z. And that's how we would rewrite that one. I go a little faster through the second one of these. Okay, 3b is okay, x squared plus y squared. Oops, there you go. All right, so z is running from 0 to x squared plus y squared. I know that when I switch to cylindrical coordinates, that's going to become an r squared. Okay. And so maybe I'll just start with that. 0 to r squared, f of r and theta and z. And we know that dv is r dr d theta dz or whatever. So r, this was z. And then, okay, well, this, okay, same situation, y being between 0 and 1 minus, the square root of 1 minus x squared means we're looking at the top half of the unit circle. But the only difference here is, okay, x is running from -1 to 1, so, you know, I'm looking at that whole semicircle. So, let's do theta next. Theta is running from 0 to pi. And r is going from 0 out to 1. Okay. So that's, yeah, we rewrote the interval. That's all we needed to do. Use cylindrical coordinates to find the volume of a sphere of radius 2a. All right. From which a cylinder of radius a has been removed. Interesting. Let's think about this one for a second. I need to, okay. Okay. And then we're going to cut, like, core out a cylinder that I guess is going to just, it's got to go halfway. Right, and then maybe that's going to be 1A. Right, so I think what I'm going to do is I'm just going to find, I'll use cylindrical coordinates for the cylinder, but I know a formula for this volume of a sphere of radius 2a, and I think I'm just going to use that, right? Okay, volume of sphere. Okay, that's going to be 4/3 pi radius cubed, which is going to be equal to, all right, if I cube 2, I get 8, so it'd be 32 pi over 3 multiplied by a. Oh, whoops. Yeah. Okay, I'll call it the cylinder. Call it cylinder C dV. To look at it from the top, the cylinder looks like this. It's got a radius of a, so it looks like that. R is going to run from 0 to a. Theta is going to run from 0 to 2 pi. Just trying to think how, yeah, I think that this part of this cylindrical coordinates would have been unpleasant. Besides, I'd use cylindrical coordinates on a sphere. And you could just use spherical coordinates, right? So, or just use the volume formula. So I'm over here, I'm going to say 32 pi a divided by 3 minus, all right. What's going on here? Z is running from, wait a second, I am kind of discounting a curved amount of area here. Right, because I was kind of making the assumption that, like, we were just going to take out like a right cylinder, but there's still some volume left over. Let me think how that would look. If we cut out a cylinder out of a sphere, the place where it lands, like the intersection, it's going to be a circle. I'm just trying to figure out, how do you know where it's going to hit? I think you might need to do some trigonometry. Hold on. Yeah, I think this is going to require some trigonometry here. And I still don't know how we're going to account for this part up here, but we will be able to find the cylinder that we're cutting out, and then there will still be these little pieces. We'll figure out how to account for that as well. I feel like that wants to be spherical, but whatever. We'll figure it out. Okay, this is a radius of A, and this is a radius of 2A, right? So 1, 2, square root of 3. It's 30, 60, 90 triangle. So I'm over here, and this is A square root of 3. But how am I supposed to do this with cylindrical coordinates, right? Because, okay, I know r is between 0 and A, theta is between 0 and 2 pi. Z runs from, maybe I'll just say over here, negative A square root 3 to positive A square root 3. I don't know what else to say. And either way, I feel like there's a much better way to go. I don't know. Because the question is not like what's the volume, it's using the cylindrical coordinates to represent it. And I feel like there's definitely something that I'm missing right here. In there and down here. I didn't draw this very well, but like I'm talking about these two regions up there, which is just a little lump that's unaccounted for. I think I'm going to just move on. So if you see what I'm missing here, either comment or let me know, or come talk to me about it in class tomorrow. But I think that, yeah, I don't know, there's something here I'm not seeing, so I'm just going to move on. Yeah, spherical coordinates, that's easy enough, relatively speaking. Number 5. Find the volume of the region enclosed by the cone phi equals pi over 3. And the sphere rho equals 2. Oh yeah, I've worked this one already a couple times. This makes a snow cone, okay? And so to draw you a picture of it. Okay, so this is the z-axis. This is the xy plane here. I don't think I'm even gonna, it's both x and y, right? It's a plane. So I'm gonna show you phi equals pi over 3. Okay, that's phi equals 0, so pi over 3 would be 60 degrees. It's gonna be pretty far that way. And then about the same thing here. And then the circle of radius 2, which I had a compass on me, but it's going to be about like that, right? What I need y'all to be able to see is the intersection here, right? This is the whole cone, the whole snow cone. It's just a really wide snow cone. This intersection here is going to be a circle. Okay, I'll draw you the diagram from above again. So that's going to be a circle. Okay. And what's the radius of that circle going to be? Okay, yeah, I remember. It doesn't matter what the radius is because the green thing is really only giving us our theta values, right? What's kind of hard to see sometimes is that, you know, because we're trying to use spherical coordinates, that's going to be a triple integral to find dv, or to find v. We're going to triple integrate dv to find that. We're just going to be integrating dv over this region I've highlighted. Okay, so this thing all is just to say that theta is between 0 and 2 pi. Okay, phi runs from 0 out to pi over 3. And rho, okay, starts at the origin and then kind of like expands out. Rho is between 0 and 2. Okay. So we can do that. We can just set up a little triple integral. Okay. Rho 0 to 2, phi 0 to pi over 3, theta 0 to 2 pi. Okay, dv is equal to rho squared sine phi d rho, d, that's phi, d theta. Okay, and now I'm just going to go get to computing. Okay, this is 1/3 row to the third from 0 to 2. That's going to be 8/3. Okay. I'll let you convince yourself of that. That's going to be 8/3. Okay, I'm going to factor out the 8/3. That would be sine of phi. I guess, you know, this with a sine of phi attached to it, but it doesn't care. Okay, sine of phi d theta. Okay, antiderivative would be negative cosine phi, as phi runs from 0 to pi over 3. Okay, so negative cosine of pi over 3 is negative 1/2 minus negative cosine of 0 would be negative 1, and that'll be positive half. So that would be 4/3 now. The integral from 0 to 2 pi of d theta, and that's going to be 8 pi over 3. That one was a little better. Spherical coordinates to evaluate the integral of f over the given region. And 1 over x squared plus y squared plus z squared. Okay, in cylindrical, that's going to be 1 over rho squared. Okay. And then the region is 5 to 25 on that. Okay, so I think these are concentric spheres. Okay, this is sphere with radius square root 5. This is sphere with radius 5, both centered at the origin. So I can see the region we're integrating over in space, but I'm not going to be able to draw it for you, unfortunately. So I'm just going to set up the triple integral. Okay. Okay, so we're going to run this integral. We're going to switch it to spherical, right? Because this is just going to be rho between square root of, rho squared between 5 and 25, which is rho between square root of 5 and 5. And, you know, theta and phi running their full ranges. So I'm going to say, all right. Maybe I'll do theta last. Theta is going from 0 to 2 pi. Phi is going to be, it's the whole sphere, so that's 0 to pi. That's the full range of phi. And then rho is running from square root of 5 out to 5. Because this is rho squared right there. Okay. Now, this function, f of x, y, and z, is 1 over x squared plus y squared plus z squared, which we know is rho squared. And dv is rho squared sine phi d rho d phi d theta. Well, then d rho d phi d theta. Yeah, actually that one's right. And 1 second. Yeah. Okay, and what do you know? D rho d phi d theta. All right. Well, this is great for us, right? Okay, we're going to anti-differentiate with respect to rho. We can factor out the sine of phi if we wanted. But that's just going to be 5 minus square root of 5. Okay. Now I can anti-differentiate this thing. I'm going to get negative cosine. Maybe I'll do this work off to the side in like red or something. So we get negative cosine phi as phi runs from 0 up to pi. And so I get negative cosine of pi would be negative 1, so it would be 1 minus negative cosine of 0 is negative 1, so it ends up being 2. Okay, so multiplied by 2 times the integral from 0 to 2 pi of d theta. So that's going to add in another factor of 2 pi. And so I'm going to have 4 pi multiplied by 5 minus the square root of 5. That's almost all. No, 6a. One more. 6b. F of x and y and z equals y. And then the region that we're integrating over is inside the unit sphere. And all three of x, y, and z are negative. Okay, that's interesting. So it's going to be like, you know, kind of, it's not the third quadrant because that's only in the plane, but it's like that area. You know, kind of below the third quadrant in the xy plane, so where x and y are negative, and then below that is where z is negative. Really, it's an octant of that sphere. So I feel like to look at it from above, it's definitely that part. Okay, and so that's, you know, theta is going to run from pi to 3 pi over 2. Okay, r is going to run from, or pardon me, rho is going to run from 0 to 1. And phi, because, I don't know, it's like the bottom half of a sphere. Okay, the positive z-axis is phi equals 0. So if I rotated down a little bit, down halfway to the xy plane, that would be pi over 2. That's the beginning of the bottom half of the sphere. So it's going to be pi over 2 to pi. So yeah. Because z is negative, I'm going to say phi is between pi over 2 and pi. And I feel like my diagrams here might not have been very good. Maybe I'll try to draw you. Okay, so this is y versus x here. Then I'm going to draw you z versus the xy plane. Okay, and then we're going to look and see the bottom half of this sphere. Okay. Sure, it's up to your interpretation, but okay, here is phi equals 0, phi equals pi over 2, phi equals pi. Okay, so we're triple integrating over this region, y. Now I need to, y dv. Okay, I need to know the conversion factor for y into spherical coordinates. That's rho sine theta sine phi. And then I'll just kind of, because all through these are numbers, so rho, yeah, doesn't much matter. I'll do theta last. Pi to 3 pi over 2 and phi. Pi over 2 to pi. And a rho from 0 to 1. Okay, and then we're interested in integrating y, which is rho sine theta sine phi. And then dv is rho squared sine phi d rho d phi d theta. All right, so we're going to need to combine like terms, right? We're going to have 3 total powers of rho, 2 powers of sine phi. Have to anti-differentiate that. Let me think. If we reverse the order of integration here, we could use a calculator for the last part. If you're like, I don't know how to anti-differentiate sine squared phi. I'm running a little low on time. I know that I've got a class about to come back in. And so I think I might do that. I might use the calculator to, you know, reverse that. Either way, I'm going to do the 3 powers of rho right now and anti-differentiate with respect to rho. So when I do that on a rho level, I'll get 1/4 rho to the 4 as rho runs from 0 out to 1. Okay, that's just going to be 1/4. So I know that I'm going to have a 1/4 on the outside, and now I'm going to integration. I have the integral from pi over 2 to pi. Integral from pi to 3 pi over 2. Okay, I've got a sine theta, just a sine theta. 2 powers of sine of phi. And I'm going to start with theta and then do phi. So that I can do that last one with a calculator, so I don't have to anti-differentiate sine squared phi with respect to phi. That's not an antiderivative you learned in my class last year, so I don't know that I might have showed you how to do it at some point along the way this year, but it's not something you have to know. Okay. Antiderivative for sine theta with respect to theta, theta's green, is going to be negative cosine theta. This theta runs from pi to 3 pi over 2. Okay, when I plug in the top, I get cosine of 3 pi over 2. That's 0. Okay. Okay, and then when I plug in pi, I'm going to get, well, negative 1. Okay, I'll be honest, I feel like I could have definitely made an error right here, but I feel like it was probably negative 1, especially because we're looking at the integral of y at some place where y is negative. I should introduce some negativity eventually. So I'll get a negative 1/4 of the integral from pi over 2 to pi of sine squared phi d phi. And I mean, it's going to be kind of sad because I did all this work getting towards an exact answer, and well, it's going to be a decimal when I write it in the calculator, but it's all right. Validating OS. Not even sure what that means. I feel like this is not my calculator, and somebody took mine and I ended up with theirs. But a quarter, negative a quarter, negative 0.25 of the integral from pi divided by 2 up to pi of sine of phi squared d phi negative 0.196. And if you want to learn how to anti-differentiate sine squared phi with respect to phi or sine squared x with respect to x, come see me before class tomorrow. I'd love to show you how. But thanks for watching.